I'm Vaishnavi, Raghavajosyula from the Max Planck Institute in Germany, and I'll be talking about IPv6 a lot today. As we know, the IPv6 is a necessity for modern day networks, yet not everything is hosted on IPv6. And why is that? One of the major reasons why IPv6 implementation is not to that extent is because of a lot of inconsistencies in IPv6 deployments. Now, these deployments could be due to a varied factors. One could be that vendor implementations themselves are the problem, or the varying level of network expertise while handling IPv6 could be a problem because handling IPv6 networks is not the same as handling IPv4 networks. Or it could be operator configuration policies. You have a bunch of different implementation inconsistencies. And the problem is we need to tackle these inconsistencies, and only then can we move on to a functioning, stable IPv6 network. And the problem with IPv6 inconsistencies is they only occur in practice. You don't see them when you're trying to test out your own network. You don't see them on your end. They're ending up on somebody else's end. That we need to solve that issue. And one key thing that we have with IPv6 is as soon as like a network operator or a no voice network operator hits an IPv6 problem, and it's really hard to debug them because they're seeing them for the first time, it's on the internet for the first time, it's easier just to roll back to IPv4 than it is to move forward or debug from there. But we have a silver lining to this. So IPv6 has ICMPv6, which is the Internet Control Messaging Protocol, and this allows us to debug IPv6 networks. It gives us a wide visibility into how IPv6 networks work, and it's one of the core functionings of IPv6. A lot of layer 2 stuff that were in IPv4 got shifted to IPv6. So without ICMPv6 working properly, the IPv6 networks won't function properly. And through this presentation, I would like to focus on one of the IPv6 error messages, which is the packet too big message. It's a key packet because, unlike IPv4, in IPv6, you don't have on-path fragmentation. So suppose we have a source here. We're going to assume it's going to be the laptop, and it's sending a big packet, which is a 1500 byte packet to the destination, which is the server, which has a link connectivity of only 1280. Then we need the packet to fragment on path, but that's not going to happen. So what happens is the packet is sent to the router, which knows that there is a smaller link up ahead, and the router then drops the packet and sends a path MTU message back, and it sends a packet too big message back to the source saying, hey, you need to fragment the packet, it's too big. And then the source sends the packet, and it finally reaches the destination. So a key part of the packet too big message is that you can see the origin, the invoking packet in the message of the ICMP error message. So you can see where it's being invoked and what is causing the packet to be invoked. So that's going to be what we can use to figure out how these packet too big messages are triggered, or where these packet too big messages are being triggered. And another thing is, packet too big is going to be the key functioning behind IPv6 networks because there is no fragmentation on paths. So if something goes wrong in the packet too big messaging, then your internet connectivity is going to go down by landslide. So we need to figure out what the inconsistencies are, because there are a lot of inconsistencies in packet too big in the wild internet. And that is the motivation behind my research, which is that I want to investigate what are the non-standard, i.e. non-RFC compliant implementations out there or inconsistencies out there that we see with the packet too big messages. And a few anomalies that we see already is that, for example, let's take a person with ill intent, and they find out that there's a router out there that has a misconfiguration in their packet too big messaging system, and then they send out a spoofed large packet with the victim's IP address to the router. The router has misconfigured rate limits, and what it's going to do, it's going to send ICMP packet too big message to the source along with other ICMPv6 messages to it and such. And so the link of the victim is going to be unnecessarily flooded with ICMP packet 2 big messages, and assume there are multiple routers with the same misconfiguration, and a person with ill intent knows that this is happening, then their entire network is going to get flooded because of this. And yes, there is RFCs that state how we should prevent this. There is RFC best practices for this, yet they're not being maintained. Intuitively, without reading the RFCs, we would want to limit or rate limit the amount of packet too big or ICMPv6 messages we get back. But that also causes a problem. So let's suppose that you're getting a bunch of ICMP traffic from a source to a point in the network. You would want to rate limit it. So the router here is going to rate limit it, but what that's going to do is it's going to drop a bunch of these necessary ICMPv6 messages, and in which a lot of them are meaningful. So the destination, which is the laptop, is only going to get a limited amount of the ICMPv6 packet too big or other messages. What this means is the laptop or the destination doesn't know what the MTU is going to be because it hasn't received a path MTU message. So it's going to keep sending packets without knowing that these packages are being dropped in between en route. So there's a lot of MTU black holes, there's going to be silent drops of packets, and a lot more inconsistency. So rate limiting too much is also going to cause massive impacts on the network. Now, this brings me to how do we define where these inconsistencies are and how can we find these inconsistencies? So for that, I have a two-step approach. So these inconsistencies could be that a no-voice operator is setting up a default configuration for IPv6 on their operating system. And the default configuration itself is not RFC standard compliant. So how are these default configurations of these operating systems functioning? And are they compliant to RFCs? Otherwise, if it's an operator that's setting up a network, what are the operator's policies and how are they differing from the RFC standards? What are the anomalies that we see there? So that is what I'm trying to find out through my research. And to do this, I'm using a two-stepped approach, the first of which is virtual emulations. Here, I take different virtual machines of different routing operating systems, and I use just a clean standard build without modifying anything, just doing what a no-voice network operator would do, which is enable IPv6, enable routing, enable forwarding, and see what the default behavior is without manipulating anything in the networking stack. And I do this for multiple OSs in a controlled virtual environment because it's easier to plug and play, see multiple systems with the same hardware architecture. And what we see here is a few of the default stacks are in fact showing some anomalies. And so through this, I can invoke the baseline standard of what a default build, a standard OS is going to reproduce. And it's easy to understand what the routing policies and forwarding policies of these operating systems are. So that answers the first question. The second question now is I would like to deal with this through active measurements. And to understand operator policies, you need to go out there in the world. You need to start measuring the real internet to figure out who's sending out what type of messages. So for that, I will be invoking packet too big responses on the real internet, and I'll be comparing the responses that I get to the actual response I should get for a path size or a link size or a packet size. Comparing that, we will be able to observe what are the differences in the operator's policies. And through this, I will also be able to benchmark the responsiveness between network paths and network areas. And it will also easily expose the ICMPv6 packet too big anomalies across different paths. And we'll also be able to uncover unforeseen inconsistencies that we didn't see when we were doing the virtual simulations, because a lot of these anomalies, again, occur only in the wild, maybe due to a mix of both of the reasons that we've talked about. And that also answers the second question of how we want to go about it. A few challenges that I've faced so far is virtualization interference. So with the first step, there's a lot of virtual machines that I've realized they don't recognize virtual networking as real networking. So what I saw is that I would see a packet go through a virtual machine, but the virtual machine cannot parse that packet, or it doesn't even recognize that packet, but I can see the packet being received or the packet being sent. And another problem that I faced so far with virtual networking is hypervisor offloading. So what happens for a normal, if we're sending a normal size packet that is well within the MTU limits, well within the segment limits of a virtual hypervisor, it's going to go through, we're going to see what we want to see. But the problem comes to when we're sending a bigger packet. Now, what we see here is that the virtual NIC is going to segment the packet without us knowing, because our packet capture is going to be before it hits the virtual NIC. So then it's going to segment. So we're never really hitting the MTU limit. So we're never really going to invoke a packet too big here. So that's a problem that occurs in most of the virtual hypervisors, and you have to manually turn that off to get this to revoke a packet too big message. And yeah, such behavior has also been reported by recent works by like Fiebig et al. And Bassetti et al. And another problem that I faced so far is that virtualization simplifies the networking a bit too much. And what I'm going to get through these virtual tests is only what I'm asking for. But then at the same time, when I'm going to the real world measurements, it's really variable. I don't know what I'm going to get. I can't predict anything. So playing with the both is one method complements the other. If we're going to find something here, we're probably not going to find it in the other. So it's the best of both worlds for me. And yes, so to finish the big picture, ICMPv6 and packet too big is what I presume to be the base behind how IPv6 networks function, and we really need to get rid of these anomalies that occur for a better functioning IPv6 network. And most of these inconsistencies occur due to misconfigurations within the networking stacks. And to measure those networkings, we need a systematic system, which I'm trying to build, and the first of which is the first step in the system is to emulate the behaviors of the operating systems, and then to figure out what are the inconsistencies in the real world, and then finally analyze whether the inconsistencies are due to the vendor problems or through operational problems. And that's the end of my talk.
Do we have questions?
So when you were looking into the errors of the path, did you also look at the application layer at any point? Because when I was in my former life in a network provider, a lot of errors actually come because of SSL and secure connections, because they negotiate end to end and they don't take into account the path. Have you looked at the application layer as well?
Application layer, no. But going into end to end and path connectivity, we're trying to look into the path MTU size and trying to trigger each packet based on the path MTU. Because if you send a 1280 packet thinking it's the biggest packet on a 1500 byte link, it's not going to make sense. So application-wise, no, we're not doing that. Yes, but I will look into it. Yeah, thank you. We did not know that maybe end-to-end connectivity could also inhibit such behavior.
Yeah, it's
understanding.
One of the biggest problems we had on IPv6 was banking. Because of the SSL, like not taking into account the path MTU, they only negotiate between server and client.
Yeah, I think that's fun to know. A new problem with IPv6.
There you go.
This is great. For the second part, which is analyze real world behavior, I don't know how you plan to go about it, but we do have a lab that has actual physical equipment. So we'll be happy to support you in terms of providing that it's really world infrastructure that you can use for that. Yeah.
I would love to talk more about this later on. Yeah, thank you.
Hi. What is the reason behind multiple packet too big messages being sent? Is there what is the rationale that leads to this problem?
Let's assume that the rate limiting goes both ways. So it's not only the source sending the router in between sending a packet too big message, but if the source doesn't learn that the packet is too big, it's going to keep sending the same size packet. And because of that, the router is just going to keep sending a packet too big no matter, because the source isn't learning that the packet is too big. That could be because there's something on path that's changing the packet size, or the source itself is not recognizing the change in the packet size. It could be two
but
factors.
there's no amplification factor there, because in the figure,
Yeah.
it implied that a 1 became 4. That's not the case.
No, what I meant by that is along with packet too big, along with the general IPv6 messages that's going on that link, you have extra packet too big messages going to the link. Historically, the reason why rate limiting was introduced for packet too big messages was because there was a lot of DDoS attacks that happened in the late 2010s. So the response to this was to a lot of firewalls just shut down packet too big messages because they kept getting a flood in those. So in that case, for that example, I tried to explain that it's flooding the network. So network operators intuitively just shut down the packet too big responses altogether.
So I was interested in your amplification, and you also mentioned DDoS. If networks are correctly configured with BCP38 and URPF, DDoS is not a problem. Are you noticing that networks, or have you tried measuring whether networks are implementing URPF for, say, IPv6, but forgetting it for IPv, or for doing it for IPv4, but not doing it for IPv6? Because if you do BCP38, you're not going to be able to have this amplification because source address is wrong, packet gets dropped on the floor. So it's interesting.
Yes. So one of the behavior is sometimes, yes, it's not implemented correctly for IPv6, and that's causing it. The other way we see it is because a lot of these a lot of, I would say, small scale no voice operators, what they do is because they don't understand, it's not only them, it's also something uplink or upstream that's causing these things. Then they shut down the responses altogether. So that's the problem. That causes MTU black holes. That causes silent dropping of packets. So you also see this. And yes, there are a lot of not only best standard practices, but there's also a lot of informational drafts on how to handle these that one could also take into consideration. Yeah.
I would be really interested in a further exploration of misalignments between IPv4 and IPv6, where best practices are implemented for historical IP, but not for the IPv6. I think there's a lot of networks that are in that boat.
Indeed.
Amazing work. Most excellent. I mean, we can discuss these offline, but I just wanted to say that I think in general, it's worth probably, I was wondering what hypervisors you were using, because I think that's really interesting to, I don't know if you put it, anyways, we can look into it. Nice. Okay. I missed that. Wow. A lot. Okay. So
I did a lot.
yeah. So that covers quite a lot of spectrum. Yeah. Probably, yeah. I don't know. Maybe we need to build our own hypervisor that disables the NIC
by default.
By default. Yeah. Or like maybe reverse engineer to figure out how to disable it. I wanted to offer for the real world deployment, like Uni could be a pretty valuable platform. We have like hundreds of thousands of installations all over the world. So I don't know, maybe this could be an experiment that we could deploy there and get some real world data of what the middle boxes are up to, because ultimately, I guess that's the thing, right? What are these pesky middle boxes doing with the ICMP messages? Are they sending like correct messages or not for IPv6?
Yeah.
And yeah, I don't know. Anyways, we should discuss this more later.
Sure.
Excellent work.
Thank you. Thank you.
Cool. We'll keep this short. Let's thank Vaishnavi for her presentation and her research.